All right. So let's try sharing your screen.
I need to also share my camera.
I mean, like, if you want, you can like switch it off, but like, why not share it if you can?
Okay.
Yes, install.
1, 2, 3.
Do you have your speakers on? So somebody might ask a question.
Mm-hmm.
On
Yeah.
Zoom.
Yeah. Okay.
1, 2, 3. Okay. And it works. Okay. Good. Oh, we seem to be it's set up. We still have a few minutes. Yeah, usually I like bring speakers here a bit earlier because there might be technical problems. With some speakers, we like struggle like for 15-20 minutes.
Do I minimize this?
Yeah, you can like hide it. Yeah, you can press this button. Oh, you stopped sharing it. Okay.
Where is? Oh, this screen.
Yeah, so you can just press the.
I have to share this screen.
So,
Yeah.
now you're sharing it. Yeah. Yeah, you can just so you can press this. Yeah, and just like drag this stuff like in the corner.
I'll just put it here.
Yes, you can. Okay. So yeah, you can switch the focus to your slides again. Okay. So that's a pointer.
Okay.
Yeah, we can take it.
Yeah, I may want to do a little bit more thing.
Hey.
Oh, hey.
Then people can see. Oh, I mean, it's okay. I'm sorry. Oh, it's too dark. Yeah, I just I forgot which. Yeah, I think that's fine. Let's that one yeah. It's clear. So this stuff is correct. So you graduated 2023 in Beijing, right?
We对的，咱们这是第一条的这个问题，因为你是用二 D 修正来计算一 D 修正，然后用你的场的这个是比较，这个场的这个分布或者比较。Yeah, 2 minutes. Or later. So do you know the fluctuation gives per subsurface function?
Just heard about.
Yeah. Okay.
Only know the common one with.
Yeah.
Lots of
Okay, that's nice.
Yeah.
Well, it's a bit related to what I'm doing now. So far else, it's me to just read this paper and the famous Steve Hawker Moss paper. Yeah. And I am confused about some.
Yeah.
I mean, basically, if you want to argue for scalar theory is true, and it's just a pure scalar beyond perturbation, and but I'm not sure if it's still a first order foundation or second order. But scalar theory that is they prove it's a weakly first order, and but I'm not sure if it's just a pure scalar. Because the perturbation doesn't work. I don't know.
You can
Yeah, generally, unless you have other things to cancel it.
Yeah, that is first order has anything.
Yeah, let's see. And they didn't say it's in so that's what I'm thinking about.
Okay, perhaps let's start. So this this week we have a pleasure to have Xu-Xiang from University of Utah, who's gonna open our semester of seminars. So Xu-Xiang graduated in 2023 from Peking University in Beijing, and now he's a postdoc at the University of Utah. So he's gonna talk about new results in geometric approach to EFT. Thank you.
Okay, thank you for introducing me. I'm Xu-Xiang Li from University of Utah, and I'm glad to give the talk here to introduce our previous work on something called geometrizing EFT matching. And this talk is based on our previous work collaborating with Xiaochuan from UCSD and Kevin from University of Utah. Okay. So my talk contains like 3 parts. First, I will give some basic introductions on what is field space geometry and some basic applications of field space geometry in phenomenology. And then I will tell why and how we accommodate the field space geometry in our EFT matching stuff. And in the end, I will use our this type of formalism to calculate 2 examples to show what kind of benefit can we get from geometrized EFT matching and also field definition. Okay, let us first talk about what is field space geometry. Let us first look into this very simple example. It is a problem from Schwannicke's QFT textbook. You can see that the Lagrangian contains the kinetic term, the mass term, and also several interacting terms. You can see the 3-point interacting term and 4-point interacting term. And if you want to calculate the scattering amplitude from this theory, you probably will derive the Feynman rules, like the 3-point Feynman rules you can write down from this term and this term, and 4-point Feynman rules from this term. And for 5-5 to 5-5 scattering, the 3-point Feynman rules and 4-point Feynman rules will give you the S channel diagrams, the T channel diagrams, the U channel diagrams, and also the contact interaction. And you can simplify these expression, and in the end, you will find that the amplitude for 5-5 to 5-5 will be proportional to S plus T plus U minus M4M squared. So you are quite familiar with that. If you set all the momentum on shell, then this one should vanish. Okay, it is not a coincidence. If you calculate other physical amplitudes from this theory, it will give you again 0 result. It is not surprising, as I said, it is because the theory is actually equivalent to a free theory. So if you start from the free theory and do such a field redefinition from phi 2 to phi, then you will obtain the same theory you get from the first line. So it is because we have the equivalence theorem. The equivalence theorem tells us that the physical observables are invariant under such kind of field redefinition. So this theory and this theory should give you the same physical output. So this is what field definition tells us. It won't affect the physical result. So the invariance of physical amplitude under field definition has many applications in SMEFT matching. So here's an example. So suppose we have a SMEFT Lagrangian containing a operators which contains the d squared phi. So you can do such a field redefinition from phi to phi prime, and this will give you some contribution coming from the kinetic term, and this term coming from the kinetic term will directly cancel the term that proportional to d squared phi, and you can using these to eliminate all the operators in the Lagrangian proportional to d squared phi, and the result is that you will eliminate all those type of operators, and in the end, you will get other operators. And you can use these techniques, the field definition, to reduce the numbers of operators in the Lagrangian, and you can reduce the very many numbers of operators onto some basis. So actually, you can use some automatic way to do that. And in our previous work, we try to use a computer program to automatically reduce any type of operators in SMEFT.
So it's not really an invariance, right? It's a covariance because you're changing the states.
Yeah, so on this type of I should mention that the G function here contains at least 5 square if you do take expansion. So the state
No, your phi are the indices, right? You have indices of
right.
So in an amplitude, the amplitude is going to depend on those indices, which are the phi states. When you go to phi tilde, it's a different state.
Yeah, but I think the transformation from phi to phi tilde at least here we only have one state, one phi. Yeah, yeah. I will say in the several slides after this, and it is actually covariant. But if you're talking about a physical amplitude, because the physical states are fixed, so the transformation from physical state and the field we define here, there's something you need to do a transformation between them, and that will make the covariant term back into invariant term.
Okay, if you contract all the indices, then I agree.
Yeah.
That's what you're going to construct later on.
Right. Okay, let us go back to the equivalent theorem. We have known that the physical observables are invariant under field definition. So it's look like the field we impose on the Lagrangian is something like the auxiliary things. So if you imagine the thing you learn from general relativity, it's like we add some coordinate system to the system, and we use the coordinate system to calculate things. And the field here somehow works in the same way. So there's some similarity between the fields and the coordinate system. So let us try, can we just take some identifying those fields as the coordinate system? So supposing we have a series with n flavors of scalar phi, and the index here is for the flavors. So those flavors, those n flavors phi will become coordinates of a n-dimensional field space, and the space is spanned by the value of phi here. And we are considering a scalar theory with up to 2 derivative terms. So for 0 derivative term, we'll have the potential, and for 2 derivative term, we'll have this one, and we will call the factor before the 2 derivatives, the G term here. So under some non-derivative field definition, also I should mention it is a local field definition. We see that the Lagrangian transform like this, and we again define this as the potential, these as the G term before the 2 derivative. And we can see how this term transform under the field definition, which we have identified as coordinate transformation. Okay, we see that first, the potential term looks like a function on the field space because we have identified phi as the coordinates, and B of phi will become some function on the field space. And the transformation rule of V just work like a scalar on the field space. And the derivative of phi then works like a vector on the field space. And more importantly, the G term here in the previous coordinate system phi, it is this, and in the new coordinate system phi prime, it looks like this. So it transforms like a 0-2 tensor. And what's more, in the well-defined theory, the G term as a metric should be positive definite. So it is quite tempting to call the G term like the metric on the field space. So we have the field space and the metric on the field space, so we can talk about a lot of things like the geometry on the field space. So it is called a field space geometry. And there are some interesting applications we can calculate from the field space geometry. So
Sorry, I'll comment on the last term, the four derivative terms. I would imagine your original Lagrangian already contains the higher derivative terms. Because right above those equations, you're saying you're imagining the field redefinition doesn't involve any derivatives.
yes.
So what's the origin of these all partial fours term? That's your original Lagrangian.
Oh, we are just ignoring them. I just added here. We are not considering them here.
Because those are higher derivative terms, I anticipate that they give you very non-special, very non-trivial additional terms and field redefinitions.
Yeah.
So let's be clear. Are you imagining your original Lagrangian contains higher derivative terms?
No.
That's what he had.
We only consider
Look at the line
zero.
above.
Yeah. So then there will be additional many more terms, even though you restrict yourself to non-derivative field redefinition.
I mean, if we in our original Lagrangian we don't have higher derivative operators, but they appear. Yeah, right.
Why do you write it down there?
Oh, I just want to mention that we set a derivative expansion and we set a truncation for two derivative here. It's kind of misleading, maybe.
Yeah, I think so. Misleading.
Okay,
But
I mean,
it
changing.
differs, right? There are two things that give you higher derivative terms. One is whether your original Lagrangian have higher derivative terms.
Right.
Second is whether your field redefinition contains derivative term.
Right.
Given that your demand is non-derivative field redefinition, I assume you don't want a higher derivative term to begin with. So your original Lagrangian shouldn't contain those terms.
Yes. We are trying to avoid them.
But can't you do a field redefinition to get rid of cubic derivative terms? And then you get to this step, and then you do another.
Yeah, the cubic derivative term. We are considering a scalar theory, so we can have only.
In the original example, you had a cubic term with derivative.
Yes, but that term contains only two derivatives, so it is contained in that term. So yeah, it is contained in the magic term.
It's cubic, but it's cubic in derivative.
Yeah.
Not cubic in derivative. Yeah. I think they have to I imagine you have to restrict yourself up to second two derivative terms.
Right.
Otherwise, you'll be very bad.
Okay, yeah, I should mention throughout the whole talk, I would just considering two derivative term, up to two derivative term, okay.
Okay, then I have two quick questions. So one is just to check my understanding. In your second example that you gave, the simple one with n scalars, can I rephrase it as saying that if I have a field theory with n scalars, you can think of it as a sigma model. And then the field and definition independence of the physics is just a statement that the physics depends on appropriate geometric invariance of the target space.
Yeah.
That's what you're saying.
Yeah.
Okay, good. Then, actually, now I'm getting worried. If you're going to say that somehow you can only consider terms with two derivatives, but arbitrarily many powers of fields, is there a case where you actually want that? I mean, normally with effective field theory, like more powers of fields come on the same footing as more derivatives. So why would it be well motivated to consider more and more powers of fields but only two derivatives? Can you comment on that?
Okay, can you say that again? I didn't quite understand the last part.
Restricting it to derivatives seems not that well motivated. So do you have some comments on that? Am I misunderstanding? You want to do effective field theory. So why is it okay to restrict it to derivatives?
Okay, so first yeah, it's a tough question. So we are doing a derivative expansion. So in some sense, derivative expansion is like a momentum expansion. So some cases you need to do derivative expansion. Okay. So in other cases, when you do like in the SMEFT we usually work on, we do mass dimension truncation. Okay. So in that sense, we can somehow throw out those high derivative terms and only limited ourselves in a restricted way and calculate things from that. So I will talk about that in the after some slides, and then you can calculate part of the result coming from those terms. So it will help you simplify part of the calculation, but those contributions from higher derivative operators will not be contained in that.
I think I'll probably become clearer as you go. So please continue.
Thank you.
I have a question. Do you want to conserve the original symmetry of the field when redefining the
When you say original symmetry, you mean like if a sigma model, you have a
field symmetry? The symmetry of the original field. Or not your sigma model or sigma model, or generally, when redefining them, do you want to still conserve the symmetries of the field of the Lagrangian aspect?
Yeah, if you if you there's a global symmetry, definitely you you should want to retain the symmetry. Okay. Okay, thanks for the questions. I will let us talk about the things we can calculate from the field space geometry. Okay, we have a Riemannian geometry derived from the Lagrangian. We can extract the matrix from the Lagrangian, the two derivative terms, so we can calculate Levi-Civita connection and use the connection to derive the covariant derivative on the field space or field manifold. Like we can take derivative acting on the potential, which is a scalar function on that. So this is the first covariant derivative, which is equal to the ordinary derivative, and second covariant derivative, and so on. We can also talk about Riemann curvature tensor, and we will soon see that those physical amplitudes will depend on these covariant term, as you mentioned. Okay, so let us first see an example to see the application of the field space geometry. Here we have two theories, and the first theory, we are only considering the two derivative term in these slides. So the first theory has a trivial metric, which is a diagonalized canonical delta. And I should mention the flavor for I goes from 1 to 4. So for the second theory, we have a scalar h and also some scalar called pi, and the flavor goes from 1 to 3. And the metric term seems quite complicated. But actually, if you are familiar with maybe standard model Higgs, you will realize that these two are the same theory deriving from the Higgs sector of the standard model Lagrangian. When you expand the Higgs doublet into its 4 real components, you will get a first two derivative term. And if you use this polar parametrization, then you will arrive at a second two derivative term. So actually, they are the same theory. But the question I want to ask is, if you are just provided with these two Lagrangian, these two derivative term in the Lagrangian, how can you know that they are coming from the same theory? While the field space geometry tells that, because these are field definition, and under field definition, there are something is invariant under that, and we can calculate it to tell the difference between two theories. So this is an example. The magic for the first theory is trivial, so we have a trivial curvature tensor. While for the second one, you can also calculate the curvature tensor, and you will still get zero. You will still get a vanishing curvature tensor. So you know that it is both of them are flat space. So you can find a coordinate system in which the metric is trivial. So there should be a field definition between theory 1 and theory 2. So you know they are the same theory. So you can calculate the geometric invariant things to tell the difference between theories. So it is first the application of the field space geometry. The second field space geometry is about the physical amplitude. We have mentioned that under the by equivalent theorem, the physical amplitudes are invariant under field definition. So if we identify field definition as the coordinate transformation on the field space, then physical amplitude should be geometric invariant. So the example here is the 3-point amplitude. At tree level, we found that the 3-point amplitude should be dependent on the covariant derivative of the potential. And if you just regard it as covariant term, then there are 3 indices for the amplitude. So the only covariant term having three indices will be the covariant derivative of the potential. But since we are going to have a geometric invariant, we need to contract it with field bounds. The field bounds will relate the field we defined here and the physical states. And to be more specific, the field bounds are those metrics that diagonalize the G term here at the vacuum. Okay. So it is for 3-point amplitude. You can do the same thing for 4-point amplitude, and it will be a little bit more complicated. You have not only covariant derivative of the potential and also curvature tensor and so on. And for 5-point amplitude, you will have even derivative acting on curvature tensor and many more terms here. But the things here is that we can, if you are calculating amplitude from a complex EFT, then this type of language helps you calculate it more efficiently. You don't need to calculate the Feynman rules, the diagrams, and calculate it one by one. You just need to calculate those geometric quantities on the field space.
Just to make sure I understand the role played by the railbands. Are they trying to enforce my Lagrange to become canonically normalized?
Right, right.
That's the only role they play.
Yeah, they can diagonalize the metric at the vacuum, so that will
normalize them.
Yeah, normalize them.
So canonical quantization for my fields.
Right.
In my new basis.
Right.
At a point. At that point, the fields would
yeah.
not globally.
Yeah. Only at the vacuum space, at the vacuum point, we are observing the physics. Okay, so it is the other application of field space geometry, and this and.
Sorry, I have a question about the corresponding field space and real space. Real space, we know there's a Killing vector, right? And Killing vector will generate conformal symmetry. In the field space of this scalar field, is there some symmetry which is knowledge of this conformal symmetry from this space-time coordinates?
Yeah, you can talk about.
Yeah, I think there's a path in this field space along which you can some knowledge of the Killing vector bench, right?
Yeah,
Yes, I'm wondering if there isn't. What's the symmetry?
Yeah. Simply speaking.
If you don't have an immediate answer, we can discuss later. But is there such a symmetry?
Yeah, it is. If you consider global symmetry, you can imagine the matrix should be invariant under the global symmetry. Then you will generate some Killing vectors that induce from the global symmetry.
So what is that symmetry?
Like the ON symmetry, I think you will have some Killing vectors, and for gauge theory, you will have those global symmetry are localized, and you will have also
just explicit some continuous global symmetry, or the binding joints, or in the end.
In the end.
I mean, in the end, there is such a symmetry, which is knowledge of this conformal symmetry generated by Killing vector in space-time coordinates. If you see the correspondence between them.
But this relies on the isometries of the bound.
There are isometries.
And I'm referring to the path in this field space along which some knowledge of the Killing vector bench, right? So again,
Are you asking for a relation between conformal symmetry, like scale
yeah,
variance?
what's the knowledge of conformal symmetry in this field space? That's my question.
Oh, well,
The symmetry finding.
That would be anti-de Sitter, but you have to choose the field in which that you get an anti-de Sitter manifold, which has the conformal.
This is how the Einstein equations rise in string theory, right? So when you compute the beta functions for the 2D signal model, they give you the Einstein equations. So it's closely related to them. So basically, this kind of stuff is like very popular in string description.
Yeah, I think the thing I can answer to you will be that we have the isometries and that can induce Killing vectors. I don't know how to explain the relation between this and conformal symmetry because I'm not familiar with that.
But there's knowledge.
Yeah, I think you can talk about that, but currently I don't think people are considering that inside field space geometry. Okay, so we have another application of field space geometry, which is kind of phenomenological thing. People have used the field space geometry to tell the difference between SMEFT and HEFT. So SMEFT and HEFT are both some popular EFT structures to describe beyond standard model physics. We can add more operators like high dimensional operators to standard model Lagrangian to describe those physics. So both of them should we should consider building blocks for both of them. So for SMEFT, we have gauge bosons, the quarks, fermions, quark leptons, and scatters. The difference of SMEFT and one of the difference of SMEFT and HEFT comes from how we describe the scatters. So in SMEFT, we have SU2 doublet with hypercharge 1/2, and it transforms linearly under SU2 cross U1. So we can use this field to construct the invariant operators on the gauge symmetry like this. So it is how we construct SMEFT. For HEFT, we don't have just the one SU2 doublet, but we have a SU2 cross U1 singlet, which is the physical Higgs we detect on LHC. And besides that, we have also 3 Goldstone bosons that under nonlinear representations under SU2 cross U1. Those Goldstone bosons are parametrized into these U matrices. Okay, so we can also use this transformation rule to derive the effective Lagrangian. So people may ask, what is the difference between SMEFT and HEFT? They can both describe the BSM physics. So I think is that from SMEFT Lagrangian to HEFT Lagrangian, you can parameterize the Higgs doublet using the polar parameterization using the physical Higgs and the 3 Goldstone bosons. But conversely, if you want to go from HEFT Lagrangian to SMEFT Lagrangian, it's not a very task, because you may come across the non-analyticity at h equals to 0, because you want to transform this term back into like this term, then you will add the non-analyticity at h equals to 0. So some general result derived from field space geometry is that we have 2 conditions for HEFT to be described by SMEFT. Okay, first is that we identify this term before this place as the F. Okay, the FH equals to 0 should have a solution. And this solution will indicate the point where h equals to 0, which is the fixed point under SU2 cross U1. Okay, so to understand this, you can imagine in SMEFT, we are expand all the operators around this point. So we don't want any non-analyticity at this point, and we want this point on the manifold, on the field space manifold. And the second condition is that the curvature and potential and their derivatives should be non-divergent at this fixed point. So this will help us fix this non-analyticity problem. So these 2 conditions will tell us if the HEFT Lagrangian satisfy these 2 conditions, then it can be described as SMEFT. But if not, then it is not described as SMEFT.
So back to the question Alexei had earlier of why you're counting derivatives, but like you're counting derivatives instead of like a naive dimension counting that I would usually expect for an EFT. And I can imagine maybe there are contexts where that makes sense, like if you were doing a non-relativistic expansion or something like that. Why is that relevant here? Like why in HEFT do I care about, like I don't care about higher derivative terms, but I do care about terms that have many powers of h?
Well, in HEFT, I think the dimension counting, the power counting it's not very clear to me, but I think people will prefer doing derivative expansion in HEFT. Yeah, because it's a somehow chiral Lagrangian, and people do derivative expansion in HEFT, and the leading order will be 0 and 2 derivative terms in HEFT.
Like, I guess I'm asking, you have terms that are like h to the fourth there, but I could write down terms which have like 4 derivatives of u or something, and in terms of dimensions, those are the same. But for some reason, you're saying we care more about the h to the fourth term, but not the 4 derivative term.
Yeah, so let me say my real point on this word. This is not about discussion of EFT per se. This is trying to discuss the connection between the field redefinition that has the geometric interpretation where which they require in the connection the finite expansion orders somehow impose those, and also this geometric interpretation of trying to find the equivalent to field theory. It's not to discuss any general EFT. So they could discuss general EFT with higher derivatives. I think the geometric interpretation will have to include many more higher order terms. And also, I think to have a geometric interpretation, you might be naive guess that, for instance, earlier when we talk about physical amplitude, I have to do the canonical quantization problem, right? But if from a perturbative point of view, higher derivative terms wouldn't affect my canonical quantization. But if I really build all the terms together without the perturbative control, that interpretation will also be involving many complex terms, which probably generate troubles for their geometry. That's my guess. Okay, that's why in the beginning I asked they need to truncate that keep 2 derivative from very beginning. I really, it's not discussing general EFT. This is really just discussing equivalent class of Lagrangians which can be transformed by field redefinition.
Yeah. So maybe said another way, your formalism can make statements about how 2 derivative operators in SMEFT are related to 2 derivative operators in HEFT. But it can't make statements about.
Yeah, I think you can understand in that way. Yeah, the field space geometry can only help you tackle things up to 2 derivatives. And if you want to look deeper into higher derivative operators, then you will need to use other techniques. Yeah, like we also limit ourselves on non-derivative field definition. So if you want to talk about derivative field definition, then you will need to talk about some functional geometry I have talked to you. Okay, it is beyond our talk. Okay. Thanks. Okay, so these are the introduction of field space geometry and applications. And next we are talking about how to apply the field space geometry in the EFT matching stuff. Okay, so first let us talk about the motivation of using geometry to talk about EFT matching. Okay, so the first motivation is that we want to know what is the EFT in terms of the geometric quantities of the UV field. So at tree level, we have some very beautiful picture of the relation between EFT and geometry of UV, and I will show them here. So we again consider that the UV is such a theory. We have only 2 derivative terms, and some direction on the field space are heavy, and we are going to integrate them out, and we will obtain a EFT of those 5 directions. At tree level, we simply just we can obtain the EFT Lagrangian by replacing the heavy field by the solution of the equation motion. And if you only consider up to 2 derivatives in the effective Lagrangian, then the thing you need to do is to replace the heavy field by the local minimum of the potential. Okay, so to be more specific, so you consider the potential is a function of not only the heavy direction and also the light direction. Okay, so for every slice of the light direction, you can find a local minimum of the potential, which will give you the value of the heavy field. And this will give you some relation between the heavy field and the light field, which will give you some hyperplane on the UV manifold. And this function of phi of capital Phi of small phi will be the thing you need to replace in the UV Lagrangian to obtain the effective Lagrangian. Okay, so these description tells you that these hyperplane will be the EFT submanifold in the effective field theory. So in principle, these generate a relation between EFT submanifold. Generate a relation between EFT geometry and the UV geometry. In the EFT, the geometry is just the geometry of UV on this hyperplane. These generate a relation between EFT geometry and UV geometry, and with the difference between SMEFT and HEFT, we can tell which kind of UV can be described by SMEFT and which kind of UV cannot be described by SMEFT. And we have provided two conditions, and those two conditions will be transformed into these two requirements of UV. Like we need if there's an actual electroweak symmetry breaking in UV, or if the mass of the new particle come from the electroweak symmetry breaking, then we cannot simply use SMEFT to describe them. So this is the first motivation of our work. We want to relate the EFT with the geometric quantity of UV at one loop level. This is just a tree-level result. The second motivation kind of come from our results of our work. So like the amplitude, we would simply expect that the EFT operators can also be resolved or reorganized in a closed form. So these are two results. So we calculate the effective Lagrangian for O and sigma model and found that if you use the geometry to derive the EFT matching, then the effective Lagrangian can be organized in a derivative expansion way. So these are 2 derivative terms and 4 derivative terms, and you can also derive 6 derivative terms and so on. Okay, the second example is that in some cases, the geometrized way to do EFT matching helps you reduce the terms you need to evaluate in EFT matching. So we use the single extended model to be an example here. Okay. So we have talked that we want to do the EFT matching at one loop, and very useful tool we can use is the effective action. So the first step we need to do is to calculate the effective action covariantly under the EFT geometry. So how do we calculate the effective action? We usually start from generating functional and do some background field method to expand the action around some background field. So, and the eta will be identified as the fluctuating field. And we expand the action at this point. And then after the Schwanter transformation, we will get the effective action, 1pi effective action. So the tree level will be the classical action, and one loop level depend on the second derivative of the action. Okay, this is the usual way we do to derive the effective action. But we don't see any covariance here. So how can we make the calculation covariant? So the thing is that we can add in the way we expand the action. So in our usual way, how do we expand the action? We want to calculate the action at this point, and we expand it along a straight line in the coordinate space, and the eta denote the distance between phi b and phi in the coordinate space, and the coefficient we get will be ordinary derivatives. But
you should be using a geodesic.
Yeah, right. That's what I'm going to talk. Thank you. So the covariant way to do this is to expand that along the geodesic. Right, the geodesic will along the geodesic, the expansion parameter will be psi some vector along the geodesic, and the coefficient will be covariant derivatives. Okay, so using this, before we know that the effective action depends on this term. If you expand the action along the geodesic, then the effective action will depend on this term. So here I show some result of those derivatives. For first derivative, we have these term, and for second derivative, we have curvature tensor and also covariant derivative of the potential term, and also a new covariant derivative on the spacetime induced by the field space geometry. And both of these derivatives are expressed by covariant quantities on the field space geometry. So using this covariant version of expansion, we will get the covariant version of the 1PI effective action, which depends on second covariant functional derivative of the action. Okay, so this will help us to derive the effective action covariantly, and then we can extract the information we want from it. If we are interested in the divergent term, then we will get an RG equation of the EFT. So people have derived what is the divergent term from this effective action. And here we again assume that the action contains only up to 2 derivative terms. Then the result will depend on curvature tensor, the potential, and also commutator between covariant derivative will again depend on curvature tensor on the field space. So these terms, these language reorganize those divergent terms into geometric quantities, which is very powerful if we want to calculate RG equations for EFTs up to 2 derivatives. Again, as I said, if you care the contribution from 4 derivative terms, it won't help. But if you are curious on contribution from only 2 derivative terms, then this language will help you a lot. Okay. So what we did is not only calculate the divergent term, but also the finite term. So we can use them to match the UV from UV to EFT, and we can see again, can we derive the effective Lagrangian using those geometric quantities like this? Okay. Okay, so we will call it the geometrizing EFT matching, and the basic thing we want to do is to find the effective Lagrangian that has the same physical amplitude as the UV Lagrangian for those light degrees of freedom. So in the EFT, we have only light degrees of freedom. So the field redefinition will be only among those light fields. So after those subgeometry of the light component will be considered here. So we won't do field redefinition in the EFT between light and heavy term because there's no heavy components in the EFT. Okay, so how do we derive the effective Lagrangian? So typically we derive it by equating the effective action of UV and EFT, and the things we want will be automatically generated by this equivalence. Okay, at tree level, we equate these 2 terms, and we have known the result. It is just replacing the heavy field. And this is covariant, and I won't go into details. Okay, and the one loop, we need to subtract these 2 terms to derive the one loop effective Lagrangian here. So again, I don't want to go into details, but to retain the covariance during the evaluation of this functional trace, you have some tricks to take. So first, you need to use method bridging to take the hard bridging expansion, which helps you derive it more efficiently. And then you need to expand the quantities into heavy and light components because in the UV theory, these Lagrangian, these derivatives depend on the geometric quantities on the whole full space, but we only consider the subgeometry. So we had to divide them into heavy and light components. And the third trick we need to use is called the covariant derivative expansion technique. It helps you retain the covariance during the evaluation of the functional traces. So in the end, we will obtain a very complicated formula which tells you how the effective Lagrangian is written in terms of the geometric quantities derived from UV geometry, like the G term, U term, and K term here. Actually, those descriptions are not very strict, but generally speaking, these contains the intrinsic curvature of the submanifold of EFT, and U term will contain potential term, and it will depend on non-derivative term, and K is something like the extrinsic curvature, but it's not very strictly correspondence. Okay, here is a review of what we did in this section. The field space geometry help us to derive a covariant expansion of the action, which can help us define a new version of the 1-pi effective action called the geometrized one, like this. And this can be calculated covariantly, and which we can use to derive the effective Lagrangian. And the effective Lagrangian contains several covariant terms, the G term, U term, K term here. Okay, so here, what I want to ask is, what benefit can we get from this type of formula? And I will use the two examples I showed previously. The first one is the Owen sigma model.
Sorry, just come back to this slide. So normally if I do a EFT matching, right, creating all the heavy mode, I know what to do, right? I can do my correct derivative expression and get my term. So so the answer is unique, right, in some sense. Why do you want to geometrize? I guess you are going to answer, but I want to conceptually answer, get the idea. Why geometrically integrating all the heavy mode measures? So all you're doing is integrating all the heavy mode, right?
Right. Okay, so first, when you do the matching, the effective Lagrangian is not unique. There will be, because the effective Lagrangian is equivalent under Fourier definition. So different matching approach may give you different effective Lagrangian, and in some approach, maybe the effective Lagrangian will be simplified, and it is what we see in the two examples.
I see. So your geometric.
We want to reorganize the terms.
Reorganize
Yeah.
It's probably going along the geodesic. It's much more efficient.
Right.
Right. So
To
it's
get the matching.
okay,
In
the
fewer
simple-
terms, it's more efficient.
Yeah.
Otherwise, you can do what you say.
Yeah.
Cool.
Typically, you can
I
do.
do all the conceptual.
Yeah.
I think you will show us example in
Yeah,
few
exactly.
slides.
Okay, thank you. So the first is about the Owen sigma model, and I will only show linear sigma model here. The capital phi is a n component vector which transform like a vector under the Owen symmetry. So also we impose the spontaneous symmetry breaking here. So one component become massive and the other n-1 become boson-bosons. And we usually parameterize the capital phi by this parameterization. Okay, and we will obtain a complicated potential term, and these are those Feynman rules derived from potential. Okay, that is you can derive the effective Lagrangian using these UV Lagrangian, and by calculating Feynman rules, those one loop diagrams, you can obtain the effective Lagrangian. And here's the effective Lagrangian up to dimension 8. We have 1, 2, 3, 4, 5 terms here. Okay, but instead we can use another way to parameterize the field capital phi here. We don't want to parameterize it linearly. We can parameterize it in a polar way. Then maybe it will show much broader symmetry. Okay, so this is what we did here. We parameterized the capital phi in the polar way and obtain a non-trivial metric, but the potential is very simple. Then using our geometrized way to do the EFT matching, we found that the one loop result becomes simpler. It depends only on 4 terms, and all of them are geometric quantities. What's more, as I said, it is actually a derivative expansion. We can calculate, we can somehow resum all the result up to some order of derivatives. That is a more efficient way if you use the geometric EFT matching. Okay, so the reason here, some of the reason here, maybe because we do the Fourier definition, which reveals broader symmetry in the UV Lagrangian, which lead to simpler potential here. And when you calculate things, you will find that all the geometric quantities have at least one derivative. So the expansion over those quantities becomes a derivative expansion. Okay, that is the first example why that is the first example how the geometric way simplifies the calculation. And the second one is about some phenomenologically interesting model, the singlet extended standard model. First, I would like to talk about the concept of UOLEA. It is called the universal one-loop effect action, and it tries to present under a general UV theory, somehow general UV theory, what effective theory looks like. So in the original version, if the UV theory looks like this, the interaction between heavy field and light field are all contained in the U term, then the effective Lagrangian can be written in those terms, no matter how the U term looks like. Okay, so what we did is to derive the UOLEA for this type of general UV. So you will have lots of terms, and all of them depend on quantities derived from UV. As I said, the U term, the K term, and also the G term. So there are many tables beyond this one. Okay, so you can use the UOLEA to derive the effective Lagrangian. For standard model plus singlet, you can write down the Lagrangian and derive the U term, as I said, in the first UOLEA version. And you find that you need to evaluate 26 terms if you start from this Lagrangian. Okay, but you can try to start from a different Lagrangian, a different equivalent Lagrangian. You do a Fourier definition in UV theory, which you redefine the heavy singlet from S to S tilde, and it can somehow eliminate all the interacting term and transform them to higher order operators, which is suppressed by heavy scales. And they are not considered in the EFT, so we can just drop them. But the thing is that after we do this field definition, we will get a non-trivial metric. So the thing is that we transform those relevant or marginal operators to a irrelevant operators in the metric, but we have a very simple potential form. The potential form contains only a mass term for the heavy field. In this new form of the UV Lagrangian, you can use the UOLEA to derive the effective Lagrangian. Okay, so in the end, you found you only need to evaluate 14 terms. It seems that the Fourier definition in UV help us reorganize the effective Lagrangian into fewer terms. So it is again some reorganization induced by the geometry.
And you don't think it has any physical interpretation?
So actually this doesn't, so to be honest, this doesn't simplify the calculation because you need to calculate many connections from these complicated matrices. And we didn't look deeper into that, and we don't think there are some physical consequence behind these.
Because another way to UV complete the nonlinear sigma model is to have change your degrees of freedom completely UV, right? Go from the chiral Lagrangian in QCD to QCD. There's no pions and there's no sigma meson in the UV, so it's a completely different theory. So your assumption here that you're always making is that the degrees of freedom
doesn't change
in the infrared and in the UV, but that's not a general assumption.
That doesn't change. So it only applies
to changing the degrees of freedom in the UV with this nonlinear transformation of S.
Okay, so for the field definition in UV, we only redefined the heavy field. We didn't redefine the light field. So the redefinition, so the reparameterization among the light field only involve light field.
It didn't involve the light field, but it should in general, right?
You mean this one or the heavy one?
I mean the redefinition in the UV should involve both fields, shouldn't it?
Yeah, it involves light field.
Oh, okay, it does,
yeah, here's the light field.
Okay.
Can you give us a feeling about the functional form of F1 H square F2 X square? Can we see the mapping? I just want to get a feeling about those functions.
Okay, I didn't put them in the slide, so they are they can be expressed as Taylor expansion of the H square, and those H square will be suppressed by the heavy mass. So in that case, we can redefine the heavy field and cancel some terms, and the output is that we will have many more higher dimensional operators, but suppressed by the heavy mass. So they will out of our consideration. But I didn't show the explicit form of them here. So they will just some how to say that the
polynomials.
Yeah, polynomials of the parameters here, if you put the truncation on the EFT. Yeah, I can show you the expression formula if you want after the talk.
In some sense, in the first line of your Lagrangian, it's almost in this form already.
Almost in what form? You mean that one, the Lagrangian?
Yeah, in this Lagrangian, the orange terms, almost in the term of the field redefined as tilde. It's just simple product of as tilde of certain power times polynomials of H squared.
Oh, why we do the field redefinition is that let's consider only the S up to S tilde term. So by doing this field definition, we can we have a free parameter coming from F0 and F1. You can use them to cancel like the terms that are proportional to S to the first. Okay, if we consider a higher power of S tilde, then we can cancel the S squared or S cubed and even S fours. So it is a cancellation order by order.
So in some sense, you already integrate out S tilde in the UV, and then
that is a tree level thing.
Yeah, you tree level integrate out S tilde in the UV already, and then you do the EFT matching in a series of pure H with many higher terms organized by the geometric interpretation.
Right, you can understand it that way. Yeah. We already did some sort of matching, tree level matching in UV. Yeah. Okay, so here comes to the end of my talk. So let me summarize the result. So we try to geometrize the EFT matching. We want to keep the covariance, geometric covariance during EFT matching and derive the effective Lagrangian written in terms of those geometric quantities. And these geometrized the EFT matching made field redetermination prior to EFT matching procedure kind of possible because we can tackle with non-trivial magic. And our example shows that the field redetermination prior to matching kind of resum or reorganize or simplify the result. Okay, so next, there are still some open questions. So it is very interesting to study why those field redetermination in UV affect the effective Lagrangian and how they did it. Okay, the others is that can we incorporate fermions, gauge bosons, or even, as you said, derivative field definition into it. So here I show some works people have done on these topics. Okay, thank you all for your listening.
The field quantities are invariant on the field definitions. Doesn't that depend on field definitions?
Doesn't what?
So there can be some field definitions that will give you a different theory. You have different degrees of freedom. Typically, when you make field definitions with derivatives, or when you have gauge bosons, you can have some field definition that change the physical sense of your arrangement. So I was wondering how to ensure that you still have the same theory after the field definition.
Yeah, that's a very important question here. We only consider non-derivative field definition, so that won't affect the physical predictions. But if you consider derivative field redefinition, then you need to, there are some conditions you need to put on the field definition to ensure the physical predictions won't change. Yeah. Because the thing we are interested in is the partition function, which will give you all the physical predictions, and the fields we define in Lagrangian is just a integration variable in the partition function. Okay, so some sort of field definition will give you some ghost contributions, and if you don't regard it as a field definition, then that will change the physical prediction. That's one of the example. There are many other things like the non-local field definition will heavily break the equivalence in some cases. That's what I know.
I think there's a criteria if your field definition is invertible, then you have the same physical distribution.
Yeah, definitely we want the field definition invertible because it's a integration variable. We don't want the Jacobian to be divergent.
So, can you give any examples in four-dimensional relativistic quantum field theories where it makes sense to allow arbitrary powers of fields, but only two derivatives? I mean, I can think of one example, which is where the fields are dimensionless. That will be true in nonlinear signal models like Carl mentioned. Are there any others? Basically, I'm asking, when do you need this formula? It seems like you need this condition, but I don't know of any examples.
Well, I think you can regard the single extent model as a case because it is a renormalizable theory. So we have only two derivative terms.
You cannot. I mean, if you call it an effective field theory, that is just not valid. No. I mean, an effective field theory, I'm allowed any derivatives I want.
Yeah, but
stability doesn't enter into discussion. It's not a relevant concept.
I mean, in it, you can redefine the field. So you have a non-trivial metric, you have higher terms, but it's still a renormalizable theory. So you can talk about a phenomenological based on this Lagrangian instead of that Lagrangian. It's some sort of case, but if you want some other cases, I cannot come up with them here. Sorry.
So that's not the way the term effective field theory normally used.
But don't they just be high order corrections with the P to the 4 with an M correction?
Well,
because
but the question is whether they. So the issue is that usually derivatives come in at the same order as powers of fields.
Sure, but in a scattering process, they're going to be suppressed by a small number. Yeah, it's not interesting.
Okay.
So it sometimes depends on what kind of question.
What kind of question you
Yeah.
ask? So that's the kind of answer I'm looking for.
Super light field, scalar field on top of the star model, and you look for something like lowering interaction created by this field. So there's high derivative terms are.
That's the answer I'm looking for.
But
That makes sense.
low derivative.
So it's not a question about. It's not a question about theory as such, it's a question about observables.
Yeah.
So for some observables, this is an excellent way to approach things. But
Yeah, you need to make sure the power counting you want to consider.
that's super helpful. Thank you.
So I had just one question. Have you thought about the target space interpretation of these things?
The target space interpretation, can you make it more specific? Sorry.
What's that?
Can you say more specifically?
Well,
Sorry.
this comes from string theory, right? Because in string theory,
Okay.
you start with 2D world sheet, you have a scalar theory, you put 26 scalars on the world sheet, you have a 2D theory, conformal field theory. But that tells you about bosonic string theory in 26-dimensional space-time. So your fields 5 have a target space interpretation as well. But the people discuss this.
Yeah. I don't think people are discussing these because actually I don't check those papers. Yeah. Okay. Sorry for that. We can talk after this.
Okay.
Sorry.
It might be useful for you because a lot of this is known.
Yeah.
Whatever that's worth.
Yeah, I also had a related comment. So you have one of your open questions about fermions, how to interpret fermions, right?
Mm-hmm.
So like in supersymmetry or superstrings, it's like no. So you just write down the superfield.
Mm-hmm.
You do everything, your geometry in terms of superfields, and fermions like automatically fit this picture very well. In the same footing as polymers. So you can like incorporate like your metric, right, express metric and stuff like that with fermionic fields. And so at least in supersymmetric case, it's like very well known how to deal with fermions in curved geometry.
Yeah, definitely sounds very intuitive, but I think actually I have shown that people talk about how to, sorry. People talk about how to incorporate fermions, but I don't think that's in that way. So
If there is another way,
yeah,
okay,
but that is what people did in their paper. So they consider such a Lagrangian. We just ignore the gauge theory, okay? So we have the kinetic term for the scatter, for the fermions, and also some other interacting terms here. So the field definition we considered from phi to phi prime for scatters, and for the fermions, they are only considering a linear field definition. Okay, and the result is that the metric is defined in this way. So I don't think it's related to the thing you proposed.
Because you write down field definition general superfield, then you expand it.
Yeah,
But
that sounds.
it doesn't have to be though that it's supersymmetric. You can incorporate fermions without supersymmetry, and then you don't get those nice relations.
Okay.
So I think that's what this is.
Yeah,
It's sort of, you want to do it in a nice way.
Yeah.
But the world might not be nice.
I just okay. Well, at least it's a framework where we can run checks. Okay. More questions?
Thank you.
So we're gonna go to the kick out for the speaker dinner. If you're interested, please let me know so I can make the evaluation.
So very roughly speaking, one of the purposes we do the definition from EFT point of view is probably including higher dimensional operator. We want to have we want to find some field bases where we have a less number of operators for efficient computation, for scaling whatever, scaling amplitude, whatever, decay rate, whatever. So, but EFT already assumes we don't know the UV completion, right? And one of the purpose of the field theory is to find to UV complete the lower effective field theory, right? So, but then if we change slightly the perspective to ask a question about the UV completion, I think it's better to have as many as possible terms to infer the new degrees of freedom, new symmetry that appears in UV theory. So I understand the strategy to ask in what basis of the field space we have a minimized number of the operators in the Lagrangian for efficient computation. That seems to be inconsistent. Yeah, it like that's good for the computation. That computation for something that happened in low energy physics, but that is, I think, in the opposite direction to what is asked from the perspective of the UV completion, isn't it? Nevertheless, I think it becomes more difficult to have a better UV complete EFT if we take such a basis, which allow you to do the most proficient computation. For example, amplitude and so on.
I don't think I understand your question. I don't think I understand your point.
So what I mean is probably. So okay, let's say we have some UV complete theory. Now we know everything. Like for example, QCD. Now I'm not saying we know everything about QCD, but let's think about the QCD and the Kaiser Lagrangian below the QCD.
Yeah, I think you should disconnect from Zoom.
Oh,
Just leave the meeting.